Good morning. I am Jaisima N, working as Assistant Professor in Civil Engineering Department of Government Engineering College, Ramnagar. In this session, I will be explaining you the design of compression member, which is the module number 5 of design of RC structural elements. The course outcome of this particular module is to demonstrate the procedural knowledge in design of RC structural elements. In session number 4, I'll be explaining you the design of axially loaded columns. Before going to the governing equation of short axially loaded tight columns, I would like to explain the assumptions regarding the strength of concrete and steel. As explained in the previous modules, the maximum design strength of concrete is taken as 0.45 times of FCK, where FCK is the compressive strength of concrete depending upon the grade of concrete used, and the strain ranges from 0.002 to 0.0035, and the maximum design stress of steel is considered as 0.87 times of Fy, where Fy is the yield strength of the reinforcement. All columns, including the short axially loaded columns, shall be designed with a minimum eccentricity as mentioned in clause number 25.4 and 39.2 of IS 456. It is hence necessary to keep the provision so that the short column can resist the accidental moment due to the allowable minimum eccentricity by lowering the design or strength of concrete by 10%. Hence, the design strength of concrete and steel are further reduced to 0.4 times of FCK and 0.67 times of Fy in order to take care the minimum eccentricity, which should not be greater than 0.05 times of the lateral dimension as stipulated in clause number 39.3 of IS 456. The minimum eccentricity should be calculated for both x direction and y direction of the columns. The minimum eccentricity is calculated by the equation effective, that is the effective length of the column divided by 500 plus lateral dimension of the column divided by 30 or 20 mm, whichever is greater. The minimum eccentricity should not be more than 0.05 times the lateral dimension of the columns. Now, coming to the governing equation of short axially loaded tight columns, as we know that the axially loaded columns are the columns where the axial load is concentrically applied on the column, and the applied load is resisted by the concrete area, which is AC, and the longitudinal steel provided, which is ASC, which is effectively held by the lateral ties at the regular intervals. By assuming the design strength of concrete and steel as 0.4 times of FCK and 0.67 times of Fy, we can write an equation as mentioned in Indian Standard Code IS 456 clause 39.3, that is PU is equal to zero point 0.4 times of FCK into AC plus 0.67 times of FY into ASC, where FCK is the compressive strength of concrete, AC is the area of concrete, Fy is the yield stress of steel, and ASC is the longitudinal area of steel provided. In this particular equation, we have two unknowns. Those are AC and ASC, which is to be determined from this particular. In order to determine the AC and ASC, the given equation is recast in terms of gross area, that is AG, the gross area of concrete, and the percentage of compression reinforcement employed. By using these two parameters, the ASC can be rewritten as percentage of steel into gross area divided by 100, area of concrete as gross area into 1 minus percentage of steel divided by 100. Hence, the equation can be rewritten as PU by AG equals to zero point 0.4 times of FCK plus P by 100 into 0.67 times of Fy minus 0.4. Hence, from the above equation, we can directly find out the gross area when the ultimate axial load and the compressive strength of concrete and the yield stress are known, and by assuming the percentage of steel, which generally ranges from zero point 0.8 to 0.4, sorry, 0.8 to 4%. Coming to the design example of axially loaded short column. In this particular problem, the column size is given as 400 mm by 600 mm, which is subjected to an axial load of 2000 kilonewton under the service dead load and live load. And the unsupported length of the column is 4 meters, and the end supports of the column is effectively held in position and restrained against rotation in both ends. And the concrete grade of concrete given is M25 and grade of steel is given as Fe 4 and 5. We need to design the reinforcement for this particular condition. So the first step in the design of column is to check whether the column is short or slender. We call the column as a short column when the effective length by the lateral dimension of the column is less than 12, then such type of column is known as short columns. Hence, the given data is the unsupported length of the column, which is nothing but 4000 millimeter, the width of the column as 400 mm, and the depth of the column as 600 mm. From table 28 of IS 456, for the given restraint, for the given support conditions, L effective X and L effective Y is calculated as 0.65 times of unsupported length, which is nothing but 0.65 times of 4000, which is equal to 2600 millimeter. Hence, we can find out whether the column is short or long or slender by calculating L effective X by D and L effective Y by B. In this particular problem, both L effective X by D and L effective Y by B is less than 12. Hence, the column is a short column. And step number 2 is to find out the minimum eccentricity. As explained to you earlier, the minimum eccentricity along X and Y direction is greater of Effective length divided by 500 plus d by 30 and 20 mm. So by substituting L effective and D in the equation, we get 25.2, which is greater than 20. Therefore, E minimum along x direction is taken as 25.2 and E minimum along y direction is taken as 20 mm. And the EX minimum and EY minimum should not be more than 0.05 times of D and 0.05 times of B. Hence, 0.05 times of D leads to 30 mm and 0.05 times of B leads to 20 mm. Since it is not greater than 30 and 20, hence we can use the equation that has been provided in clause number 39.3 of IS 456 for the design. So we can use the equation PU is equal to zero point 0.4 times of FCK into AC plus 0.67 times of FY into ASC. Substituting the given data into this equation gives me the area of longitudinal steel as 2238.39 millimeter square. So by providing 6 numbers of 20 mm dia and 2 numbers of 16 mm dia bar, the area provided is 2287 millimeter square, which is more than 2208.39. The thing that we need to remember over here is whatever the area that has been calculated, the steel provided should be slightly higher than the area required. And the dia of the bar should be decided depending upon the area, depending upon the number of steel. The minimum dia of the bars in the column should not be less than 12 mm and maximum dia of the bar can go up to 32 mm. In Indian market, the standard diameter of the bars available are 6 mm, 8 mm, 12 mm, 16 mm, 20 mm, 25 mm and 32 mm. So by using 20 combination of 20 mm and 16 mm diameter bars, we are providing an area of 2287 millimeter square, which is more than the area required. The percentage of steel is 0.953%, which falls within the range of 0.8 to 4%. Hence, the provided steel is okay. So from this, what we can understand is the percentage of steel should be between 0.8 to 4%. Under any circumstances, the percentage of steel shall not be less than 0.8 and shall not be more than 4%. In order to hold the provided reinforcement effectively, we need to calculate the lateral ties and what should be the spacing of the lateral ties. As per clause 26.5.3.2 of IS 456, the transfer reinforcement shall not be less than maximum dia divided by 4 or 6 mm. 6 mm. Since in this particular problem, the maximum dia provided in the longitudinal reinforcement is 20 divided by 4 or 6 mm, whichever is greater. So the diameter of the bar used as lateral tie is 6 mm. As per the clause of 26.5.3.2 of IS 456, the pitch of lateral ties should not be more than the least of, first one, the least lateral dimension of the column, which is in this particular case 400 mm, and second one, 16 times the smallest diameter of the longitudinal bars to be tied. In this particular problem, the smallest diameter used in the longitudinal reinforcement is 16 mm, which leads to 16 into 16, which leads to 256 mm or 300 mm. The least of these three is 256 mm. Therefore, we are providing a lateral ties of dia 6 mm at the spacing of 250 mm center to center. This completes the design of axially loaded short column. Thank you.